So we talked about integers. Remember, there was this sort of amazing thing. We discussed how computing integers evolved. But of course, we didn't cover all the necessary things. And as we will discover during this course, there are lots and lots of things about integers which you need to know, but probably do not. Not just you. There are even things about integers I should know, but don't. We discussed a different representation of signed integers. We sort of ended the class with the discussion of two complement integers becoming the de facto standard, yes? But of course, as is the case with most things in computers, old things come back. For example, some of you might wonder, why do I need to know about one complement? Why do I need to know about a sign magnitude representation of integers? Well, let me give you an example. Sign magnitude integers are coming back, but in a different context. As we will discover later in the course, people eventually realize that fixed size integers are not necessarily the only way integers are represented. Sometimes you want to have variable size integers, right? 1 byte or 2 byte or 3 byte, or as long as you need. And then the question arises, how would you represent signed quantities? If you use two complement, it affects the length of the integer in a very undesirable way. For example, think about it. If you take number 2, it's a clearly, or 5, let's take 5. It's clearly a 1 byte quantity, fits into 1 byte. However, if you take minus 5 as a 2 complement 32-bit quantity, it immediately becomes 4 byte quantity, 4 byte thing. You cannot drop 0 bytes as you can in case of 5. So what happens, and we shall see it in more detail later, that if you want to represent signed integers of variable size, we will have to go back to sign magnitude representation, representing sign, and only then representing variable size unsigned quantity, magnitude. Right? So, which means that even those old techniques are coming back. This is why it's important to know what happened in the past. It will come back again, invariably. That's my experience. For example, we might not want to know that some computer called Stretch allowed you bit addressability, but you do not know if bit addressability is gone forever. It might come back. Maybe not on my lifetime, which is probably could be measured in months in terms of computers, but for most of you, it just might come back. But there are two other things about integer representation which we need to address, which we didn't. Well, there are more than two, but two other characteristics of fixed size integers. Okay? One which was very, very important and still remains very important is endianness. Again, this is something which apparently sort of needs to be decided. When people realize that they can represent integers as a sequence of bytes, the question arises, how do you represent, say, 2-byte quantity, 16-bit integer? in memory? Do you use the first byte, the byte with the lower address, as the least significant byte, or is more significant byte? And at first, the question appeared self-evident because there's one solution. Remember who introduced byte addressable memory as the main thing? It was IBM with its 360, and the 360 designers had a very clear understanding of how to do it and what's the right way. They decided that putting the more significant byte first, or most significant byte first, was the right thing. Big endian, you put big byte, the most significant byte, as the first byte in memory. And it would have been good if everybody just followed the trend. But people didn't. A great split happened, roughly speaking, around year 1970. There were two competing parties. There were parties which said, we will follow IBM, big endian, and there were people who were saying, no, we will do little endian, and the most important thing historically was, of course, a little microcomputer company called Intel, which decided that little endian is the way to go. And by the way, anyone knows what is the literary foundation for these two parties, whom they were referring to? Yes, Gulliver Travels. Yes. And there was a vicious war, and it still, even today, still goes on. There are people who are in this camp, there are people who are in that camp. If you do networking, sadly enough, you have to deal with big endian things because many of the network protocols were designed by sort of big endian people. And if you program on Intel machines, as some of you do, you live in the little endian world. What do you think is the right solution? Anybody has an opinion? I'm okay. Jerry says it has to be one of them. Everybody agrees with Jerry? How? Oh. No, but in the future, what should happen? Well, that depends, again. This is an interesting question, which goes to the question of how it's a good observation. As you see, in some sense, we write numbers backward. Never mind computers. We do. Because if we write 123, we write 123. That is, of course, depends on the way you read. But we, of course, yeah, well, you followed your, Arabic friends. But it is a good argument, and in many respects, as we shall see, little endian has many advantages. But what do we do with all the big endian data? Is it illegitimate? You see here what happens, and that's what I'm trying to sort of, the message is that you don't have to have a unique encoding. In some sense, both encodings are legitimate. Jerry is wrong. In other words, he says only one is legitimate. But no. I mean, you could have a big Indian 64-bit integer data type. I'm not talking about existing programming languages. I'm talking about what is a data type. It's a way we interpret bits in memory. We could interpret them this way or that way.
But if it's fixed size and you look at the big chunk first, you know how big it is. But if it's variable.
I agreed with you that there are some advantages of little endian. But what I'm saying, the encoding, it's again, the point is, are there advantages of two complement integers? Yes. But is it the only legitimate way to represent integers? No. That's what I'm trying to say. And big endian and integers is in encoding. And any encoding is a legitimate encoding, guys.
What makes something legitimate? Only if there's a reason.
Well, there is a good reason to use it. There's a lot of data which uses this encoding. That's what makes it, what makes Hebrew a legitimate language? Well, the people speak it. Right? That's the fundamental thing. Otherwise, you say, what is a language? It doesn't even have vowels. Huh? But there is a solid reason for viewing Hebrew as a legitimate language. All the people who speak Hebrew, all the people who wrote in Hebrew in the past. Yes? And the same thing with this encoding. This is a bogus thing. We cannot just say, let us forget it, because there is data encoded in it. It's a legitimate encoding which should be viewed, again, what I'm trying to say, let me put it in a very, very basic way. We tend as a community to develop parties based on utterly insignificant things. Like you go and ask somebody, like, say, Ryan, what's the right editor? And his eyes shine and he says, Vim. And you ask, say, Nick, and he says, Emacs. Am I correct? BB edit, whatever. So, and the only thing I'm trying to say that, guys, these are just different interfaces to the same thing, processing, strings or whatever, right? And the same thing with big endian. These are legitimate encodings. People use them. There's lots of data. So this is the endianness is not. You should not view it as these people are bad people because they're big endian. This is just not right. This is a very simple message. But then finally we have to get to another attribute of integer encoding, which is nowadays usually not even known, especially by people who use modern programming languages, such as, say, as Ilya would say, Java. He's so proud of being modern. Anil too. Those modern people. The modern people do not know of this property of integers called alignment. How many of you know what alignment is? Half. Okay. So while it seems, and what we shall see, it's a thing to know, but a thing on which the modern people, such as Anil and Ilya, might be right in the long term. Because what alignment means is that certain types, such as, say, integer, might be required, this is a very careful thing, might be required to to start with address divisible by 4. I'm talking about 4 byte integers. Then this 4 is the alignment of this type. Right? Anybody knows why alignment appeared? What was the reason for it? Meaning? Observe that everything was addressable. Since IBM 360, every byte is addressable. So why would you need to know this thing called alignment?
The physical machine could only fetch a particular, even though the address exists.
Fetch what? A machine could fetch a byte from any byte address.
Faster operations?
It could fetch that set of bytes in one operation if it was aligned.
That is a precise thing. That starting from sort of 360 byte addressability allowed you to fetch a byte from any address. Right? That was not true for a word. Word, and what is a word, by the way? Anybody knows what a word is? Natural size of the machine. You don't have to assume that there are things called registers. But you sort of assume that machine has a natural, what does it mean, natural size?
The instruction set deals with that in some optimal.
Close, but there is even better way of saying it. Yes. I mean, there is the natural size of how much you actually can fetch. Right? You could fetch less, but there is the one operation fetch, say. So remember, there were 16-bit machines, then there were 32-bit machines, there were 64-bit machines. What it means is that how much the processor fetch, again, I'm simplifying things greatly at this point, were growing. That's the natural size. And what happened was that for most machines, they would allow you to fetch an integer only from properly aligned address. You could fetch a byte from any place, but you could fetch a word or fetch an int only from properly aligned address. Sort of for many architectures, you would get what if you do otherwise? Bus error, right?
Address error. Bus error when the bus doesn't deploy.
You would get, on HP it was called bus error. Or at least that's what the message you would get. And that was a property of most RISC machines. Sort of RISC architecture assumed that only aligned load and stores should be implemented. It was viewed as sort of the right thing, because doing unaligned thing would require to do two operations. You first need to sort of imagine that things are unaligned. What do you need to do? You need to bring two adjacent words and then do some kind of a shift in hardware. And that was against RISC. RISC means minimal, reduced.
The idea is that if you want to do that, just write the instructions to do that. Why make your machine do that?
Right? Because, again, the goal of RISC was to make all the instructions, as we shall see, the goal right now appears to be utterly strange, let me put it like that, all the instructions to be short and uniform. Like in the older machines, say IBM 360, there were instructions which will take that much time, that much time, that much time. There were non-uniform instruction lengths. So RISC were aiming, at least for load store instructions, to have very uniform things, which again sort of was a dream because then caches appeared. So it became as non-uniform as we will see as possible. So uniformity disappeared. But the goal was to have simple instruction set with what we will discover, and this is, again, I'm giving you a little preview of what we will eventually see, that things change dramatically. One of the great things which Intel was able to do, all of you probably know that Intel is not RISC. And all of you probably know that Intel architecture is dreadful. Okay, so I knew 20 years ago. So did most people who even worked for Intel thought. It was assumed in the, say, mid-90s that Intel architecture, 8088, 8086 architecture, was doomed. Intel invested many $1 billion in coming with a new architecture, well, or they bought for this new architecture from HP called Itanium. It was clearly understood by everyone that Intel, as it was then, couldn't survive past, say, the year 2000. I participated in many high-level meetings with top corporate executives, everybody agreeing that Intel is, old Intel architecture will be dead. And believe it or not, the company which saved Intel architecture was not Intel. You know who turned things around? AMD. They actually somehow decided that you can prolong the life of Intel architecture. And they designed what is known as IA3264, 64-bit extensions of Intel architecture.
Well, I think they also had some help from just Itanium being amazingly complicated and taking twice as long and all of that. I remember some compiler researchers calling it the Lifetime Employment Act for compiler writers. It had all the features you can think of.
This is true, but the remarkable thing was that from that point, so say around the early 2000s, it became clear that there is some future in Intel architecture. But then, and I hope to demonstrate it practically to you guys, is that Intel guys did something wonderful, remarkable, and astonishing. They made this architecture very competitive, so competitive that all the RISC architectures had to disappear. Right? And part of the thing which they did, it's only one part, there will be very many things sort of behind this fairly ugly instruction set with which they started. They developed fantastic microarchitecture. And one of its great accomplishments was, and that is not commonly known, is their beautiful handling of unaligned reads, which has major algorithmic consequences. That is, Intel right now allows you to read integer from any boundary, or 64-bit, effectively. It's not as fast as if it were aligned, but it's almost as fast. And in practical contexts, it's often allows you to trade very expensive branches. What we will discover is branches are really the killers, not unaligned load stores. And you could trade unaligned loads for branches and get huge performance gains. We will look at it later in the course. So in any case, alignment of integer is another property which you need to know. Now we're going back to the question which I promised, which we will address, and is comparison of different programming languages.
Oh, just before you leave integer representations, I thought of one other basic integer representation
Okay?
that is still being used, and people should think about it.
Yes. No, but no.
It's representing a signed number using an offset. So, for example, the exponent field of a floating point number is usually represented with the number added on. That's sort of half the total range. So maybe it goes from minus 128 to 0 to plus 128, but that's represented as 128 is the value 0, and 0 is minus 128, and so on. And that has advantages that it's very easy to sort. You can treat it as an unsigned thing, but it sorts correctly, which is, I think, relevant because that makes sorting floating point numbers a little bit easier. If the exponent is at the left and the fractional part is normalized, you're sorting it by its numerical magnitude without doing as much work. Isn't that right, Alex?
It is right, except floating point compares are awfully fast.
Because of all the special, yeah.
That is, okay. I do not need it. So, yes, but not really for floating points as we have them now. Sort of what happens, and this is I think this is a very, very important thing, that as we look at the sort of the progress, what happens is the different trade-offs constantly change. Once upon a time, floating point operations were expensive. As we shall see, they're less and less so. That is, they're operating on doubles is becoming so fast. Intel got so good with that comparing two doubles is fast enough. What we will also discover that our old idea that if you do in your algorithm, you do two things like this and that, then the complexity is the sum of these two quantities, is no longer true. The processors are not doing one thing at the time. Sort of, we will be studying it with.
But as an algorithmic technique, I think that's a very useful thing to know.
Yes.
Your range and
yes. That is the important thing. The technique is important. If it's not important for double, it doesn't matter. It's an important technique to know. It's like signed magnitude representation. It's not important in the sense, no computer you buy is going to use it for signed quantities. But it's an important representation to remember because you might use it yourself. Right? So all of these techniques, which appear to be obsolete, are not really obsolete. They're algorithms. You have to know them. One day you might use them to great benefit. That's why it is important. Okay, so now let us look at some. So what we will do, we will look at some benchmark, and the idea is we want to see how we could sort of compare different languages. And we're going to look at a very simple task. We're going to sort integers. And you say, why sort integers? Well, sorting is, first, a well-understood problem. Second, it's a very important problem. For example, Knuth, when he was writing about sorting in the early 70s, in his third volume of The Art of Computer Programming, remarks that 60% of all computer time in the world is spent on sorting. When I talked to our present boss, Brian Pinkerton, You might have heard of him. He says, what's search? It's just sorting. Remember, this is the guy for him constructing of an index is more important than queries. You know why, right? Because he was the first guy in the world who actually came up with an idea of constructing an index for the entire web. He built the first crawler. So for him, it's not a bad thing to do. So obviously for him, sorting was the central operation. It still is for us when we construct an index. Because when you do query, you don't sort.
You sort. You find what matches, and then you sort by whatever you want to.
Yes, you do. Yes, you do. Yes, you do. But to finding match set, you don't need to sort.
Yes, but the important thing is ranking the match set, without which the match set is not useful.
Yes. I agree. So, thank you. Sorting is important even on the query side. So, but it's a well understood thing. So, what we would like to see is what are the ramifications of using different languages. So what we did, Param and I, we wrote 3 pieces of code. We wrote a piece of code in C++, this old ancient language which is despised by modern people. Then we rewrote the code in advanced modern programming language called Java. And then we rewrote it in a futuristic programming language called Python. Yes, of course, that's right. And okay, so we will look at that, but before we look, let me sort of tell you 2 things which we discovered. First thing which we discovered is that they're remarkably identical. Sort of what we wrote, the code, is sort of indistinguishable. If you have a couple of glasses of vodka, you couldn't tell the difference. It just looks the same. Right? And we could have done them even more so because we decided against writing Python with parentheses. Sort of, but if we did, it would look, even Python would look as if it were Java. So all this stuff about, programming language is a programming language. The fundamental constructs which you use are called if, while, they're the same. Even in a modern programming language such as Java, if does the same as in Algol 60. There hasn't been much development since then. There was development from Fortran to Algol 60. What was the development?
Tri-state if. Tri-state if. Arithmetical if.
It was, yes, it was arithmetic if. So Fortran till Algol 60 was the first language which had Boolean if. Sort of if else. In Fortran it was if negative 0 or positive. By the way, who invented this if? Who suggested it for Algol 60? I know that you know, but this is a curious thing because very few people would know that the person who suggested if for Algol 60 and who was one of the inventors of Algol 60 was John McCarthy. The guy who invented Lisp apparently was one of the American representatives on the Algol 60 committee, which was a rather marvelous committee, had very many, at least 1, 2, 3 of them won Turing Awards. No. Dexter was not a member of the committee. He was right there, but he was not. He was talking to them. But so it was a mighty committee with lots of brilliant people. And again, McCarthy was the one who convinced them to put if. And if remains there. So let us look. So what we will do, we will walk you quickly. We're not going to analyze the code deeply. We will eventually discuss these algorithms later in the course. But right now we will just show you the code and then run the benchmarks based on the code. So every benchmark contains the algorithmic part and then the driver which runs them. Okay, and we will change places. Or could you Param will lead the code expedition.
So, of course, yes, go ahead.
They are non-stable.
This is quicksort. And so that we can compare in a fairer way, we decided not to use a generic quicksort for C++. We took our previous generic version and converted everything to I believe, int64, if in the final version. Yeah, it's all int64. So that's what we will be showing here. It's a quicksort int64.
Why did we do it? One of the reasons is that we wanted to compare apples with apples. And obviously, modern programming languages cannot have generic code. Well, Python can, but the great language Java does not allow for such niceties as genericity, at least not if you write sorting algorithm. So we had to sort of move code back so that we basically made the benchmark in a way to make it as advantageous for Java as possible. Right? And what we shall see, we actually are going to praise Java to high heavens as a result of that benchmark. So if you use Java as if it were Fortran, it's actually a good language.
So actually, this is an important thing to note. We are going to look at strictly sort of low-level algorithmic code. And for that kind, the claim is for that kind of code, whatever language you write it in, it looks like Fortran, effectively.
Yeah, or Algo 60 or whatever.
Okay, so we're not going to go through this in detail. I'm just going to give you the high level, yes.
Even more.
It fits
Yes.
so far. Okay, so of course at the, should I start at the top, you think?
Shrink it much more so that we could see, just shrink it a lot. Because they don't really need to know the code yet. They need to, but then make the window large and shrink it much more. Because what I'm trying to show is what are little algorithmic pieces. Then we will compare them side by side a little bit later on. We'll look at, say, Java versus C++. Right now, we're just looking at C++. So, okay.
Okay, so we start with, we need insertion sort at the end, at the bottom layer of quicksort, right? So we start with insertion sort. There are basically, a bunch of utility functions. There's unguarded insert. There's a guarded insert. There's unguarded insertion sort. There's a guarded insertion sort. So those are 4 insertion sorts. We have a function to compute median of 3 numbers, which is what you need to compute your pivot in quicksort. And this, in fact, I think translates without any changes whatsoever to Java. It's identical.
And very, very similar in Python. Not identical, not identical.
You have to delete the types. Yeah. OK, then you get to the heart of quicksort. Here's the unguarded partition algorithm, which takes a pivot and starts from both ends, finds elements that are in the wrong positions and swaps them. So that's your unguarded partition. Is the main quicksort loop, which finds the middle, finds the pivot by calling median of 3, and then calls unguarded partition on both sides. So the way we've implemented it is we look at which of the partitions is smaller. For the smaller one, we make a recursive call to quicksort loop, and for the other one, we just iterate in the same context. And that's basically it. This is the top level thing that called.
By the way, anybody knows why we do that? Yes, so why, yeah, but why do we choose the smaller one for the recursive call? To assure that then, well, termination will happen in whichever way we do it, but that guarantees that what? That our stack size is, yes, very good. It's logarithmic stack size. Because you see if we're very unfortunate and we probe, and every time we just split, say, one guy. Then we could have linear stack. Is it likely? No, it's awfully unlikely, and in practice will never happen. But nevertheless, and we have, as we will discover, algorithmic techniques even to account for that, which we're not using here. But this is the standard technique to assure that you never need more than log n stack size.
So in all, it's about 90 lines of fairly straightforward code.
Could we look at Java side by side? Is there some way of placing the same thing?
New window.
Of course, Java experts tell us that we don't know how to write Java, but they don't make any specific corrections. So the attitude is that you have to spend decades to study Java to be able to write a simple loop. We didn't have decades. But the story is true. That's what we were told.
So here is the.
You could go down, all the way down. It will be sort of instructive, I think, to compare from the bottom. You see, of course, we have to make all of these public static members of some bogus class, because the modern people don't believe that function could exist by itself. That would be awful. Not object-oriented at all. So we put it someplace, we make it public static to whatever, and then observe. It's fundamentally, of course, they have no pointers because that would be unsafe, and modern people don't believe in pointers. But we take two indices and a long array. The modern people do not believe in 64. They use a much more precise word, long. I don't know. It's just that's how they are. Of course, they guarantee that long is in 64. But
so the translation, in fact, was pretty literally for all pointer arguments, introduce an array and offset. And then change all the calls, put public static in the beginning. That was basically it, I think. Maybe there are one or two other things that we'll.
So it took us, roughly speaking, 15 minutes. Not for one function, for the entire file.
Yes.
Is the C++ being compiled as 32-bit or 64-bit?
This is on 64. This is 64.
Yes. Nothing we could do. Java does not allow 64-bit indexing into arrays. It's a modern language. They do not believe in long arrays. It was designed when everything, Sun didn't know about 65. I mean, only advanced companies as SGI had 64-bit. So, you know, int is nothing we could do. In C++ being an archaic language, your container could have different size types, but they don't know that. They'll discover it in about 30 years.
Of course, the other thing you have to do is anytime you're dereferencing the pointer, you have to, index an array.
But
Other than that, there's a line by line.
It's identical. We can. But it's not, I mean, we were trying to be reasonable. In the sense, we try to use idiomatic Java, idiomatic C++, and idiomatic Python. We're solving the same problem. We're sorting 64-bit integers, right?
So here's unguarded partition, pretty much the same. A median of 3 is literally identical, I think.
Let us just look. Yes, short of long in 64 change, there's no change.
And here are our insertion sorts, the same 4 that we had before. And again, you can see it's pretty much the same thing, except that you're dereferencing an array instead of indexing an array instead of dereferencing a pointer.
We should look at Python code, I think. We could replace C++ window with Python. Actually, probably not. We probably should eat. Then we will look at Python code after lunch.